All right. Speaking of laws of chemical combinations. So again, related to chemistry because chemical combinations. So different laws that govern it. So 5 basic laws. You have law of conservation of mass. This you're very familiar with. Law of definite proportions and law of multiple proportions. You guys had studied this when we were talking about atoms and molecules. How many of you remember this? If you don't, it's okay. Like I'll go over it again. But how much do you remember? I just want to know. Not at all. None of you.
Law of conservation of mass, you're asking?
No, I'm talking about definite proportions and multiple proportions. Okay, we'll do this again right now. And then you have Gay-Lussac's law of gaseous volumes. So Gay-Lussac was a scientist who worked on gases. He has another law called Gay-Lussac's law. It is different from Gay-Lussac's law of gaseous volume. So mentioning this is important. And then you have Avogadro's law. So this is again it's not kind of connected to the mole concept, but yeah, Avogadro law is different. Fun fact, speaking of Avogadro's number is named Avogadro's number not because Avogadro worked on it. It's that number, somebody else worked on it. It was like a whole team. There was a whole evolution behind it, but they wanted to honor Avogadro for his contribution. That's why they called it Avogadro's number. Okay. Yeah. Starting with law of conservation of mass. What is law of conservation of mass?
Mass can neither be created nor be destroyed.
Absolutely. So what happens to mass if it can neither be, it's not created or destroyed?
Stays constant.
Yeah, the number stays constant. It's just transformed from one form to another, especially in chemical reactions. So if let's say I take some coal and I weigh it and it weighs like 50 grams, then I burn it and there's ash remaining, right? If the mass of ash reduces, what does it mean? Does it mean that the law of conservation of mass has failed? What does it actually mean?
It was converted into other forms, like some of them could be liberated as gas.
Very good, yes. So if you see that there is change in mass, it means that you haven't taken into account something. Like if the mass appears more after the process, it means that, oh, it took some from the gases or whatever. And if it appears less, then some of it has escaped as gases. Yeah. Okay. But law of conservation of mass is always conserved. The total mass before reaction is always equal to the total mass after the reaction. All right. Law of definite proportions. So like law of definite proportions, law of multiple proportions seems very obvious. It's like common sense now that you guys have studied about different elements and compounds. But at the time that this was defined, imagine this. So this was at a time when people were not familiar with the concept of atoms and molecules. So it was like kind of groundbreaking, which is why it's one of the basic laws. Law of definite proportions was proposed by Proust. So what the law mentions is that states that a given compound always contains exactly the same proportion of elements by weight. So if you take a compound, like again, let's go with water. So whether you take water from your Bisleri bottle or tap, or if you like go to the seaside and take some water, wherever you source that water from, water is always water. It will always contain hydrogen and oxygen, and the quantity of hydrogen, the ratio of quantity of hydrogen to quantity of oxygen will always remain the same. Okay. Rishit, you mentioned 2:1, which is correct when you're talking about it in terms of number of atoms or like the moles of the quantities. But when you're talking about mass, like Proust said, they contain exactly the same proportion by weight. So then, yeah, you have to calculate it based on the weight. Okay. So Proust, obviously, like he didn't work with water when he stated it. He worked with copper carbonate. So he worked with 2 samples of cupric carbonate, one of which was natural origin, like he found an ore or something from the earth, and the other was synthetic, something that he created in the laboratory. And when he analyzed both the samples, he saw that the ratio of copper to carbon to oxygen was always the same, whether it was natural or synthetic. So he said that, oh, if there is a compound, then it will have the same elements in the same ratio by weight or the number of atoms. Okay, so that's important. So if the ratio changes, if the ratio of copper to carbon to oxygen, any one of these number changes, then it's no longer the same compound, it's a different compound, that way. And law of multiple proportions is again related very closely to definite proportions. So this was proposed by Dalton. So he says, if 2 elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. Okay, so this sounds a little complicated, but the context is, okay, all of these was proposed, Dalton proposed this in 1803. Proust proposed his own law like way before 1803. So at this point of time, there was no concept of atoms and molecules as such. People didn't know that, people knew different elements existed, but they were still formulating their ideas of atoms. It was not discovered yet. So think of it in that context. Like if you didn't know that water was made of hydrogen atoms and oxygen atoms, how would you explain what water molecules were, right? So definite proportion says that water to oxygen ratio is always going to be 1:8, hydrogen to oxygen by mass. And Dalton says that you have 2 elements combining to form more than one compound. Like the example given here, you've got hydrogen, like water and hydrogen peroxide. Water is H2O and hydrogen peroxide is H2O2. So you have 2 elements, hydrogen and oxygen, combined to form more than one compound. So this is compound number 1 and this is compound number 2. Then the masses of one element that combine with fixed mass of the other element. So which element has a variable mass in this context?
Oxygen.
Yes, Rishit. So in both cases, the mass of hydrogen is fixed. Like if you consider hydrogen 1 gram, there's 2 grams of hydrogen combining with 16 grams of oxygen here, and 2 grams of hydrogen combining with 16 into 2, 32 grams of oxygen here. So the masses of the one element that combine with fixed mass of the other element. So if hydrogen is fixed, you take the mass of this other one, which is combining with hydrogen. They are in the ratio of small whole numbers. So 16:32, ratio is 1:2. Okay. So you will never get a ratio like as long, like the main criteria is that this should be fixed, the other element. 2 grams combined with how much? 2 grams combined with how much? Or 5 grams of hydrogen combined with how much? 5 grams of this combined with how much? So the other element, this needs to be fixed. So if you compare the masses, you will always get small whole numbers. You will never have ratio of 1:1.5. Like this does not exist. It's always going to be like 2:3 or 1:3 or 1:2, like that. I'll take another example. Carbon and oxygen. What are the 2 compounds that these 2 combine to form?
Carbon monoxide and carbon dioxide.
Yes, carbon monoxide, carbon dioxide. 2 different compounds formed from the same elements, carbon and oxygen. So if you take this case, what is the fixed mass of carbon with which oxygen is combining?
One.
Mass of carbon. One atom, yes. So one atom of carbon means how many grams? Like what's the mass?
12.
12 grams, yes. This is something you guys need to brush up on, huh? At least the first 20 elements. So 12 grams of carbon. In case one, how much of oxygen is 12 grams combining with?
8.
16.
16. 8 is the atomic
16.
number. Mass is 16, yeah. And in the other case, how much is 12 grams combining with?
32.
32. So if we take the ratio of oxygen, you've got 1:2 again. This is pretty obvious. Let's look at the two oxides of iron. So one oxide is FeO, ferrous oxide, and the other oxide is Fe2O3. All right. So what do you think the ratio of oxygen is going to be in this case? Now, because the quantity of iron is different, you'll have to like do some mathematics to make it similar, because you need to check what is the mass that's combining with a fixed mass of other element.
Is it 2:3?
Yeah. So you get 2:3. So they're always in like small whole numbers. So this gives you a clue, like if they're whole numbers, if you're not getting like half at like that told Dalton that, oh, so things are made up of atoms with fixed quantities of mass. So 16 grams, like oxygen is always combining in multiples of 16. So he was like, so atom must be made up of particles that are each 16 AMU. So that's kind of how they pieced it out of what is the world made up of, something called atoms that way.
So, ma'am, how was Fe2O3 that one? 2:3? I did not understand that.
Sure. So you need fixed quantity of iron, right, to see the ratio of the other variable thing. Over here, there is one atom of Fe. So if you, to make it constant, if you take double of this, so 2 into FeO, then like iron ka weight is around 56 or 57. So 56 into 2 grams of iron ke saath, how much oxygen is combining? 56 into 2 grams of iron ke saath, how much oxygen is combining? So that's how you get 2:3. It's literally like if you had to just make a guess of it, you just like that gives you the ratio of the number of atoms of that substance that's combining, kind of like that. Is that clear?
Yes, ma'am.
Okay. Cool. So yeah, so that's how like when people started figuring out that hydrogen is always combining in multiples of 1, they're like, okay, so hydrogen ka mass is 1 atomic mass unit. Oxygen is always combining in multiples of 16. Oxygen ka mass is like 16 atomic AMU, like that sort of thing. Now comes Gay-Lussac's law of gaseous volumes. So Gay-Lussac observed that, like again experimentally, when gases combine or are produced in a chemical reaction, they do so in simple ratio by volume. So when gases combine, this is gaseous volumes, right? So exclusively for reactions involving gases. When two gases combine, or if there's a gas being produced in a chemical reaction, they do so in a simple ratio by volume. So when it comes to gases, he's talking about the volume of the gases. So why do we talk in terms of volume of the gases is completely based on how gases are stored. So how do you think gases are stored?
In cylinders.
Compressed.
Cylinders. Yeah. Compressed, or however, like you take them in cylinders, right? And airtight cylinders, yes. So those cylinders are fixed, they're airtight, they have a definite volume. So the measurement of gases is mainly through volume. So they do so in a simple ratio by volume, provided that all the gases are at same temperature and pressure. Now this is the most important part, because when temperature or pressure changes, the volume of the gas changes. There's a relation between the temperature and the pressure. Okay, think of it. Temperature is pretty easy to visualize. So hot air balloons, right? Like, have any of you seen a hot air balloon being filled? Like if you had a deflated balloon and then that needs to be filled up. Smira has seen it. Like, how does that happen?
Like somewhat like parachutes only. It
Yeah.
just gets bigger suddenly. It's
It doesn't get bigger on its own. So somebody's
like
doing
this.
something to it. So what they
The
do
air
is
is occupying the space.
air needs to, something needs to push the air to occupy the space, right?
There's like a fire, and then that
Ah.
increases
Yes.
the size.
There's a fire. So what that fire is doing is it's heating up the air around it. So that air, it expands and makes the balloon expand, and a deflated balloon slowly fills up. I'll pull a video up and I'll show it to you guys. Let's see. Filling hot air balloon. Let's see video. Yeah, Ritisha is saying flame. Yeah, so the hot air basically fills it up. Okay, here they're like directly blowing it out. So there's other ways where it's like lying down, and then they heat up the air so that it expands, it fills up the balloon, makes it inflated, and then they slowly heat it up so that it fills up the rest of the balloon like that. So yeah, increasing the temperature increases the volume, because the air literally expands the thing. So that's how volume changes when you change the temperature. Pressure also affects the volume. The best example is a syringe. All right, I'll just let this finish. So yeah, once you have enough air, it occupies the whole of the hot air balloon, and that's how it's filled up. Okay. All right. So how does pressure affect the volume of a gas? Is how many of you guys have seen a syringe being used, or an air pump to fill balloons, to fill your cycle tires, right? So syringe, Ritisha, a lot of you have seen it. Okay. Come on, guys. Again, quite a few of you have shut down your video. Suzanne. So how do you operate a syringe?
By pushing the thing.
You pull it back and then
Yeah, and
you
then
push it.
pushing it.
Yes. So is the syringe empty, or does it have like some amount of air or whatever? If you take an empty syringe,
air.
Air.
there is air inside. And when you push the syringe, what is happening? Are you pushing the air out, or like what's
You're
happening there?
applying pressure.
You're applying pressure, you're increasing the pressure. So what is happening to the volume of air that is already trapped inside the syringe?
It escapes and decreases.
If you seal the other end of it, the volume essentially decreases. Like even though you have the same quantity of air, like if you have it sealed, you can still, you're basically like reducing the volume. Another way to look at it is if you guys have played with balloons. Have you squished a balloon without it blasting? No? Okay. Some of you have. So balloon is fixed in quantity, but you apply pressure, you squish it down. No air escapes, but the volume of the entire air decreases. So basically, having the temperature and pressure constant is important to maintain the volume. If you change any of these, the volume is going to change. That's why this is important. So at same temperature and volume, like let's say you're keeping that constant, when gases combine or produced in a chemical reaction, they do so in a simple ratio by volume. So simply put, basically he's giving the relation between the volume of a certain gas with their composition. Like basically if you have hydrogen gas and oxygen gas, because we know that water is H2O, we know that the ratio between the number of hydrogen atoms to oxygen atoms is going to be 2:1. But before, if you didn't know that about the existence of atoms, the only way you could figure this out was checking how many tanks of hydrogen have combined with how many tanks of oxygen to produce like this much amount of water. So they saw that if you took 1 liter tanks, like 2 liters of hydrogen always combined with 1 liter of oxygen, like that. If you took 100 ml tanks, then 100 ml of hydrogen always combined with half. It always combined in the ratio 2:1, whatever volume you took. So that's what Gay-Lussac mentioned. And Avogadro's law is related to the volume of a particular gas. Equal volumes of gases at the same temperature and pressure should contain, like they always contain equal number of molecules. So whatever gas you take, as long as you maintain it at the same temperature and pressure, like this example given, you took it at 273 Kelvin, 1 atmosphere pressure. If you took 22 or like 100 ml of any gas, if you measured its mass and then figured out the number of molecules that it contained, you always got the same number of molecules. Yeah, equal volumes of gases at the same temperature and pressure always contain equal number of molecules. So by extension, experimentally, people found out that at standard temperature and pressure, so this is something you guys will come across frequently. It's called STP. STP just stands for standard temperature and pressure. So the standard is basically atmospheric pressure, 1 atmosphere, and at 273 Kelvin. So these constant values, so these are, it's called STP. At these particular values, the measured volume for 1 mole of any gas, if you took 1 mole of helium or 1 mole of oxygen, 1 mole of nitrogen, 1 mole of hydrogen, whatever gas you took, they always occupied 22.4 liters. So this value, note it down because a lot of calculations will be based on this. Like you will need to know the number 22.4 liters. You'll be using it in a lot of calculations. So at STP, whatever gas you take, 1 mole will always contain 22.4, or the volume of 1 mole of a gas will always be equivalent to 22.4 liters. And this is applicable only for gases. Doesn't matter which gas. If you see STP, 1 mole means 22.4 liters. So by extension, if I had 128 grams of oxygen at STP, how much volume will it occupy? Calculate it.
And when we say STP, we mean that all of them have the same temperature and pressure.
Yeah, at standard temperature and pressure. Like standard means like standardized to a particular constant value, which is 273 Kelvin and 1 atmosphere.
These are the, we always take STP as 273 Kelvin and 180.
Yeah. So it doesn't matter which gas, the logic is that 1 mole at STP will occupy 22.4 liters. Okay, so based on this, like let's say I have 128 grams of oxygen. If I maintain it at STP, what is the volume this gas of oxygen is going to occupy?
22.4.
1 mole occupies 22.4, but I don't have 1 mole of it. I have 128 grams. So how much is that going to occupy? Wait, before this, how many of you remember mole concept? Just like raise your hand.
I do a little.
Little, okay. How many of you like have absolutely forgotten it? 1, 2, 3. Just keep your hands raised, no? Like I'm looking at all. Oh, 1, 2, 3. Rishit also has raised hand. 4, 5, 6. Okay. All right. So let's do this. Like I'll go over this first and then, yeah. Oh God, without mole concept, you guys wouldn't be able to answer this question. Just realize that. Okay. Arnav 89. So Arnav, can you tell me how you calculated it?
It was given 38.0 grams is 1 mole. So
38.
120.
How did
30,
you get?
yes.
How did you get 38?
It was given in that previous slide.
Oh, I think this is like too tiny, but oxygen's molar mass is 32 grams. Okay, so that's 32. I'll just zoom in and I'll show it to you. Yeah, there you go. 1 mole of O2 is basically 32 grams of O2. Yeah. All right, so let's say, okay, you took 38. So how did you calculate it? Yeah, go ahead.
128 divided by 32, we get 4.
Okay, you did.
Into 2.
Yeah, 128 divided by the molar mass. So this gives you what?
1 mole of oxygen.
This
right?
is this gives you number of moles. Right, and then you multiplied this by 22.
22.
You're absolutely right.
89.6.
Yeah, your logic or the way you approach this is absolutely right. Kritisha also got it, Smira also got it. But of course, it needs some fine tuning to figure out like what is 1 mole mean and, you know, this division and all that. So we'll go over that now. Okay. So 1 mole is basically used to describe quantity. So it is similar to how doesn't means what?
Well,
12.
12.
12 of something, right? Like it could be dozen eggs, dozen oranges. It could stand for anything. Basically, dozen is number of something. Similarly, 1 mole is number of something. So this something can be either atoms or molecules or ions, particles, whatever it may be. You can extend it to benches also, but practically, obviously, that's not how it works. Just like how dozen is 12 of something, 1 mole stands for 6.022 into 10 raised to the power 23 of particles. Particles matlab atoms, molecules, ions, depends on the context, electrons, anything. Now, how does this relate to chemistry is like experimentally it was found out that 1 mole, the relation between 1 mole is number of this much. It is also equivalent to the mass of the particle in grams. Yeah. Like usually if you were measuring mass of atomic mass, then that's atomic mass units, right? Mass of molecules also, it's the number of protons plus number of neutrons, that's AMU, right? So if you take that number, in place of AMU, if you express it in grams, that is equal to the mass of 1 mole of the substance. So basically, if you take 1 atom of carbon, if you measure its mass, so that's basically equivalent to 12 AMU, atomic mass units, because there's 6 proton plus 6 neutrons, whatever. Like basically, do you guys remember the numbers, mass number, atomic number, all of that? Yes, no? No? So do you guys remember what is an atom, like what it is made up of?
neutrons, protons, and electrons.
Neutrons, protons, and electrons.
Neutrons, protons, electrons, right? So do you remember what are like the properties of neutrons, protons, electrons? So what is the property of a neutron? Like how would you describe it? What sort of a particle is it?
It's a neutral particle. It has, okay.
There's no charge.
No charge.
Yes,
Electron has negative charge. Right?
that's awesome, cool. So neutrons are neutral, no charge. Electrons are negative charge, and protons have
Positive.
Positive charge.
positive charge.
Positive charge.
Okay. What can you say about the bulk, like the mass of neutron, proton, electron? Do you guys remember that?
A minus that and all those.
It's equal to number of protons added to the number of neutrons, right?
The atomic number minus the mass.
Yeah, like that's the concept I need you guys to recall. But the logic, or why we have these concepts is that you have neutron, proton, electron. Neutron has charge 0 and it contributes to mass. So neutrons and protons are massive particles, like at the subatomic scale. So these two contribute to the mass. So neutron has like, each neutron, we take it to be like 1 unit of mass. That's what atomic mass unit is. And each proton, you say, okay, 1 unit of mass, because they're approximately equal mass particles. Electrons are, even though the charge is same as proton, it's like extremely tiny, that its mass is negligible. You don't count the mass of electrons. So like neutrons and protons, the mass is to the order of 10 power minus 28 kg. And electron ka mass is 10 power minus 31 kg. So it's like if neutron was scaled up to be 1 kilogram, electron would be like 1 gram. It's like if we had like a sack of rice, then electron would be like a grain of rice. It's like that much of a difference, which is why we neglect the mass of electrons. That's why when you talk about mass of atoms, it is number of neutrons plus number of protons. Yeah. So yeah, carbon contains 6 protons, 6 neutrons. That's why it is 12 AMU. And because of protons, for every proton you have an electron, atomic number is equal to number of protons. That is why, Ritisha, you were saying number of neutrons is mass number minus atomic number, because you're taking total minus the number of protons. That's why you're getting the number of neutrons like that. Okay. So yeah, so 1 atom of carbon is equivalent to 12 AMU. But if you take 1 mole of carbon atoms, so if you take 6.022 into 10 power 23 atoms of carbon, and if you weigh it, its weight is going to be 12 grams. That's kind of the relation. So 1 mole is equal to the mass of the particles. If you're taking atom, it's going to be atomic mass of the particle in grams. If you take molecule like water, it's going to be molecular mass, but expressed in grams. Like if you have oxygen, 1 molecule, if you look at a single molecule, its mass is going to be 32 AMU. If you take 1 mole of oxygen molecules, its mass is going to be, the number is going to be the same, the unit will be grams. That's the concept. Yep.
1 mole of oxygen molecules, so that will be 6.02 to 10 to the power 23 molecules.
Yes, correct. So if you count the individual number of molecules, this is basically equal to 6.022 into 10 power 23 molecules. Okay, so this is what the whole mole concept is. So you relate moles with the number of particles with the mass of those many particles. Okay, so it's like whatever you take uska mass and express it in grams, and that becomes the molar mass. Molar mass is basically 1 mole ka mass. So this is called molar mass. This is atomic mass, molecular mass. Molar mass is the mass of 1 mole. That's all. Okay. We'll just like do some practice just to refresh you with this concept. Do you guys remember the formula for calcium carbonate?
CaCO3.
CaCO3.
Awesome.
CaCO3.
CaCO3, made of calcium, carbon, and oxygen. Can you tell me what is the molar mass of calcium carbonate? If you need help remembering any of the atomic mass, molecular mass, let me know, I'll give the value. Otherwise, calculate it and tell me.
What is the atomic mass of calcium?
Calcium is 40, right?
Yes. So calcium ka atomic mass is 40 AMU, carbon is 12, and oxygen is 16. Ritisha, yes, number is correct. And what unit will you use for this?
AMU.
Molar hai.
Gram.
Grams, yes. Awesome. Shreya, correct, absolutely right. Ritu, got it. Rishit, what happened? Check your calculation. You missed out on one thing. Kaveri, check your unit. We're looking at molar mass. Matlab you're taking a whole mole of it. Yes, now we corrected it. Correct. Adit got it. Kaveri corrected the unit. Rishit, yeah, you figured it out what happened. Smera got it. Yes. Awesome. Excellent. Calcium carbonate is made up of one calcium atom, so that contributes 40. One carbon atom, that contributes 12. And there's 3 of oxygen. So you multiply 3 into 16. So each oxygen is 16, 3 of them. So you multiply. So you've got 100 total. If it was one molecule, it would have been AMU. But because you're taking 1 mole of it, so many of them, this will become grams. Yeah. All right. So one step extra. What would be the mass of 3 moles of CaCO3? Awesome. Yes. Ritisha got it, Ritu got it, Kaveri got it, Smera got it. This is simple, like unitary method, right? 1 mole ka pata kiya, so 3 moles ka kitna hoga? Arnav got it. Adit, yes, absolutely. So 1 mole is 100 and 3 moles is unitary method. 3 into 100, 300. All right, let me twist it some more. How many moles in, I'll keep it simple. Um, 560 grams of calcium carbonate. Ha, Ritu, now you got the hang of it. Good stuff. Yes. Smera, got it? Yes. Sanat, I hadn't like send your answer. Adit, yes. Rishit, correct. Adit, no. That is wrong. Check your calculation, Adit. 1 mole is 100 grams. If you have 560 grams, how many? And don't round it off because these are simple calculations. This is 560 in case it's not clearly visible. Arnav got it, yes. Who else is yet to answer? Kaveri, no, check your answer. Acha, Kaveri, can you tell me how you solved this? Let's see where you're going wrong.
So in 3 mole, if 300 grams is 3 moles,
Okay.
so 1 gram would be okay, I know where I made a mistake.
So, okay, who's yet to send? Shreya, Sanat, Rishit and Ritisha both sent. Kaveri sending. Arnav, Adit. Adit, you also corrected. Kaveri, yes, you corrected. Good stuff. Rishit is asking, when do we use 0.22 into 10 power 23? That is when you have a question about the number of molecules. So if I say, how many molecules in 560 grams, then you use Avogadro's number to figure out the number of molecules. Okay. All right. Calcium carbonate. I wanted to start off simple for you guys. So where is this? And I took it step by step. So now I'm going to give another question, which is going to be like a tiny bit more complicated, but related to the same concept. You guys, you should be able to do it. Change up the compound. how many moles in um, hmm, let's see. It's not G, 119 grams of ammonia. Oh, Sanat, okay, you missed it. So, till how confident are you with mole concept, Sanat?
Ma'am, not much because like it's been a while since
Absolutely, yeah.
since I did it.
So, when did you get disconnected? At what point?
It's been like 5-6-ish minutes.
Like, what's the last concept that you remember?
I remember hearing about the calcium carbonate part. That's all I remember.
Oh, okay. So, we're just doing practice. So this is a sequence, like calcium carbonate you see on the board. This is the formula. Find out first what is the molar mass of calcium carbonate. And after that, directly skip to this question, how many moles in 560 grams of calcium carbonate? And then answer this question, how many moles in 119 grams of ammonia? If you're stuck somewhere, let me know. I'll discuss it with you.
Okay, ma'am.
Ritisha, yes, correct. Smera, yes. Nitrogen is 14 AMU in case you're stuck there. Rishit, yes, correct. Shreya, got it. Good. A little bit of rekindling and you guys are able to solve it. Like that's all there is to mole concept. It's all unitary method. That's it. And this is like one of the really important concepts because you don't have an explicit chapter. Like this is the only chapter where you would work on this explicitly. Other physical chemistry chapters like equilibrium, there's a chapter. It expects you to be able to do these calculations. So this is something that you need to know, you need to keep in your mind. Kaveri, check your calculation. Smera is correct, Adit is correct, Ritu is correct.
Ma'am, can you explain this one?
It's the same as what you guys did for this particular problem. So step 1, figure out what will be the mass of 1 mole of ammonia. 1 mole equal to how many grams? Once you get this, you have a relation like n x grams will be equal to 1 mole. 119 grams will be equal to how many moles? Always mole concept may figure out what is the molar mass, how much is the mass of 1 mole of whatever is the given thing. You get your base thing. After that, if you have to find the number of moles, you have the relation unit for unitary method. If you have to find the number of grams, you still have the unitary method. Sanat and Arnav, absolutely right, you got it. Kaveri, yes, now you got it. Did you do it the other way around? Did you multiply 100?
Yes, ma'am, I made a really stupid mistake.
Yeah, just be careful, like see what units are given. So again, always follow this. Figure out what is given, what you have to find with units and everything. Then you'll avoid these kind of mistakes. Okay. Cool. So that is it for mole concept. Now applying Gay-Lussac's law. So I had asked, if I have 128 grams of oxygen, how much volume is it going to occupy? And your base relation, like at STP, of course, this goes without saying. And your base logic, according to Gay-Lussac's law, is at STP, 1 mole of any gas will occupy 22.4 liters. So this is like your concept. So using this, figure out how much volume 128 grams of oxygen occupies. Yes, Ritisha. Calculation, I'll have to check, but I think it is fairly correct. Yeah, answer is correct. Other, check your calculation. See if you've used atomic mass of oxygen or molecular mass of oxygen. Because we're talking about oxygen gas, it exists as O2. So you need to consider O2 ka mass for this calculation. Ritu is correct. Yeah, Adit, I think here's where you made a mistake. Like when we talk about pure elemental oxygen, your mind should always go to, oh yeah, oxygen gas matlab exists as O2. So always consider O2. Rishit, yes, you are correct. So Ritisha, Rishit, Smera, Ritu, Adit, you've corrected it. Now you got it. You're right. Shreya, I think you did a similar mistake as Adit. In your calculation, consider it to be O2 and then do your calculation. Kaveri, you got it. That's correct. Sanat, yes, correct. Shreya, have you figured it out? What happened?
Yes, mom. I'm multiplying it with 4. I did it with 8.
Yeah. So O2, right? So what do you guys get? What is the molar mass of oxygen?
32 grams.
Of oxygen.
32 grams.
Of oxygen, it's 16. Of O2, it's
Of
32.
oxygen, 16.
When I talk about oxygen gas, then consider it as O2 only. So molar mass. In this context, we're talking about oxygen gas, right? Like you will never find individual oxygen atoms just existing. So default, consider it to be O2. So molar mass is 32 grams. So that means 1 mole is 32 grams. Figure out 128 grams is how many moles? How many moles?
4.
4.
4 moles.
4 moles. After this, it's like 1 mole is 22.4 liters. So if you've got 4 moles, it's 22.4 into 4, 89.6. Cool. So based on Gay-Lussac's law, these are the kind of questions, problems that you're going to get. Okay. Dalton's atomic theory. Yeah, so based on all of these findings, Dalton published 1808 May. He was the first one to postulate that matter is made of small particles, are called atoms, and atoms combine to form molecules and like certain fixed ratios. That's all said. So atomic mass, we just discussed what is atomic mass. So the formal definition for atomic mass is based on the carbon-12 isotope, because that's like largely available and you can easily measure it because carbon is a solid. So it's like defined to be 1/12 of 1/12 of 12 grams of atomic of carbon-12. Okay. There you go. Atomic mass is mass unit equal to exactly 1/12 of the mass of one atom of carbon-12. Average atomic mass. So right now, if you Google for atomic mass of any element, Google the atomic mass of zinc and tell me what you get. If you like, I'm sure you guys have your phones with you, right? Or if you're using the computer, just open a new tab. Hmm.
65.38 U.
65.38 U or AMU, that's atomic mass units. But I just told you that atomic mass units means number of protons plus number of neutrons. So why are you getting a decimal number there? Any idea? No idea. Okay. Do you guys remember what do you mean by isotopes? This word.
They have the same number of protons but different number of neutrons.
Correct. So isotopes are atoms of the same element. If they have the same number of protons, they're essentially the same element, right? Same number of protons, but different number of neutrons. So this, if you have the same number of protons, different number of neutrons, what does it do to your atomic number and mass number?
You'll have the same atomic number but different mass number.
Yeah, you're gonna end up having same atomic number but different mass number, right? So isotopes are elements that have the same atomic number but different mass number. So best examples, you have carbon existing, like you have a C12 isotope and C14 isotope. So C14 isotope is radioactive because it's not stable. That's what is used in your radioactive carbon dating of fossil fuels and all of that. But yeah, so these two are isotopes of carbon. C12, if you take 1 mole of it, will weigh 12 grams, and C14, 1 mole of it will weigh 14 grams. So to account for all of these, like you have in the universe, you have both C12 and C14. In order to figure out like a universal atomic mass, like yes, so you take the average of both of these. So average meaning like you don't take simple average. It's not 12 plus 14 by 2. It is something called weighted average. So basically the average atomic mass that you calculate also takes into account universe mein how much C12 do you find and how much C14 do you find. Okay, like if 99% of the carbon weighs 12 AMU and only like 1% of it weighs 14 AMU, your average atomic mass is going to be closer to 12. It's not going to be, it's going to be farther from 14. So something like that. So the calculation that this follows is, oh good. So you've got C12, C13, C14. The relative abundance, like how much of C12 you have, 98.892% of it is carbon 12. 1% of it, 1.108 is carbon 13. And 2 into 10 power minus 10% of it is carbon 14. Right? So the average atomic mass of carbon, if you Google it, you're going to get something like 12.0 something. So how you get that decimal number is you take the relative abundance, 98%, matlab 0.98 times 12 AMU plus 0.01108 times iska mass, that's 13, plus 2 into 10 power minus 12, like whatever remaining, times 14. Okay, so this is how you calculate the average atomic mass. So if I had to give you a formula for it, it's going to be something like, so average atomic mass is percentage abundance, like whatever abundance it is, like 60%, 40%, whatever you get, percentage of abundance into mass, like abundance 1 into mass 1, plus percentage abundance of the second isotope into the mass of that particular isotope, plus and so on, like how many ever isotopes you have. something like that. So, okay. If you're still noting it down, cool. Like for example, if you had 67% of one isotope of M1, mass M1, and remaining like 33% of mass M2, then your formula is going to be, you won't multiply it by 67 because it is percent, you will multiply it by 67 by 100. So 0.67 into mass 1 plus 0.33 into mass 2. That's how you do it. Okay. Then molecular mass is, it's the mass of the whole molecule. So it's like sum of the masses of the individual atoms. Formula mass. Any of you remember what formula mass is? This also has come up in grade 9. Any idea? No? Okay. So when it's, okay, what is the main difference between ionic compounds and covalent compounds?
Ionic compounds completely donate or take the electrons, whereas in covalent compounds they share.
Okay, conceptually, yes, covalent compounds may sharing happens. Ionic compounds may, the fact that they donate electrons is wrong, like it seems that way, but ionic compounds primarily are made up of ions. Ions are formed by losing electrons or gaining electrons, and losing electrons will form what kind of ions, positive or negative?
Positive.
Positive.
And gaining electrons will form?
Negative.
And
Negative.
if you have a positive ion and a negative ion, what do they do?
They attract.
They attract, like positive and negative opposite charges attract. So that's how ionic compounds are formed, because a positive charge and a negative charge attract each other. That's how ionic compounds are formed. So as a result, if you see, it kind of looks like, oh, this one lost electrons, this one gained electrons, oh, this one must have given it. But that's like a wrong, like that's not actually how it happens if we get down to it. Yeah. So that part is important because that leads to how ionic and covalent compounds exist. Okay. Now, because covalent compounds share electrons, covalent compounds can exist as independent molecules. You have one molecule of water, second molecule of water, third molecule of water, like they're all independent molecules, right? You can have individual molecules. But when it comes to ionic compounds, the positive and negative charge, they don't exist in pairs. Okay, cation attracts anion, anion attracts cation. So each anion is surrounded completely by cations, and each cation is surrounded completely by anions. This is, since this is a screen, I can show you a 2D structure of it, but this is what happens in a whole 3D structure. Like there'll be another anion in front of it and behind it also, that way. Okay, so in this context, do you have like a well-defined molecule? Like, can you identify one molecule of this ionic compound? Like considering all of them are, they're all held together because of the attractive forces between unlike charges. But can you identify any single molecule in this?
I didn't get it.
No? So, okay, so ionic compounds are formed based on attractive forces between cations and anions, right? I'll tag them clearly differently. Let's say the cations are pink. Like if you take any ionic compound, like you take ionic compounds are mostly solid in nature, like they're crystal. Like imagine rock salt, that it's literally like that, right? Calcium carbonate, that's like chalk or limestone, rocky crystals in nature. And the reason why they are solid and they're crystals is that their structure is basically, it's a three-dimensional structure where all these ions are just held in place by their attractive forces. Okay. So every cation is surrounded by anion and every anion is surrounded by cation in a 3D structure. I'll pull up an actual structure and I'll show it to you. So structure of NaCl. It kind of looks like this, what you see here. So if you zoom in to your salt, this is how it is. Like different ions, all of them are attached or connected to each other in this way. So the purple ones are sodium ions and the green ones are chlorine ions, anions. Yeah, so they're all arranged very closely, all of them sticking to each other in this way, which is why ionic compounds are solid. Now within this, can you isolate or identify a single molecule? Like if this is NaCl, you write NaCl as NaCl like this, right? Can you identify a specific molecule of NaCl?
No.
No, like if I can't say that, oh, this is one molecule, this is one molecule, because no, like these two also are attracted and connected to each other. But in covalent compounds, because you have a set number of atoms combining with each other, they exist as independent molecules. You can separate out molecules, you can identify separate molecules in them, which is not the case with ionic compounds. So this is where your formula unit mass comes into picture, because you can't define a molecule for ionic compounds. So where are you going to get molecular mass from? If a molecule doesn't exist, it doesn't make sense to like talk about molecular mass, right? So that is the reason there's a separate concept called formula unit mass, which is basically you take the formula, like if you had sodium chloride, it's NaCl. The formula states that one, like the ratio between sodium and chlorine is 1:1. So formula unit mass of NaCl is, if you take the formula, based on the formula, you calculate that it is mass of sodium plus mass of chlorine. So similarly, MgCl2 is an ionic compound. The ratio of magnesium to chlorine is 1:2. So the formula unit mass for magnesium chloride will be mass of Mg plus 2 into mass of chlorine, because you're basing off the mass of the compound on the formula rather than the actual molecule of it. The
Mass only for ionic compounds.
Yes, the formula unit mass makes sense for ionic compounds. So the technique of calculation is the same, like that's what you're doing for covalent compounds also, but the logic behind it is different. It's just staying true to form. That's it. That's kind of it.
What does the M mean? Like M, Mg, and MCl?
Mass.
So what does that
mass
mean?
of magnesium, like atomic mass of magnesium plus 2 into atomic mass of Cl.
All right.
So that's the significance, or that's kind of why the concept of formula unit mass exists for ionic compounds, because molecular mass doesn't make sense for ionic compounds. It's used for measuring molecular mass of entities which do not exist as a single unit. So when you can't isolate a single molecule of it, that's when you use formula unit mass. Mole concept and molar masses, we just revised it, Avogadro's number and all that. Percentage composition. Okay, this is very simple, it's very obvious. Percentage composition is what percentage of the compound is composed by a particular element. So mass percentage of each constituent element. So again, if we go back to calcium carbonate, so calcium carbonate is made up of what all elements?
Calcium, carbon, and oxygen.
Calcium, carbon, oxygen.
Yes. So percentage composition is basically what is the percentage of calcium you can find in calcium carbonate? What is the percentage mass percentage of calcium? What is the percentage mass percentage of carbon? And what is the mass percentage of oxygen? As simple as that. So can you guys quickly calculate what is the percentage composition for each of these elements?
40% for calcium.
Awesome.
12% for carbon.
And
Yes.
48% for
And-
oxygen.
And 48 for oxygen.
48% for oxygen. It's simple. So mass percent of oxygen is how much mass of oxygen do you have in calcium carbonate? 3 atoms. So that's 48 AMU. Total mass of 1 unit of calcium carbonate is like 100 AMU and percentage of this. That's all there is. That's it. Okay. That's so using the percentage composition. Okay, imagine you are analyzing some rock, like you want to see what all minerals are there in the rock. So based on that, you can figure out, oh, can I take iron from this? Can I take gold from this? But to do that, you need to know what is there in the rock. So to know what element, what mineral, what ore is there in the rock, obviously no one has X-ray vision. Like using analysis, only you will figure out what elements are there. So what people do is, in that analysis, you end up getting, oh, a particular 50-gram sample of a rock has 25 grams of element A, then 30 grams, 39, sorry. Let's say 13 grams of element B and 12 grams of element C. So using this indirectly gives you the percentage composition. So using percentage composition, you can figure out what is the formula of that particular element. You know that it consists of ABC, but how, and once you know what ABC are, like that also you can do it with experiments, like make it react with water, you'll know whether it's a metal or non-metal. Make it react, like burn it, and then you'll know based on acidic or basic, like what kind of thing it is. So based on the percentage composition, you can figure out the formula, like is it AB to C or A to BC, or is it ABC, or like what is the formula of that particular compound? Okay. So that kind of analysis. So you have questions based on that. So directly from the percentage composition, you'll get something like the empirical formula. And from that, you can also calculate the molecular formula. So empirical formula is, it represents the simplest whole number ratio of various atoms present in a compound. So an example is, do you guys remember what is glucose? The formula for glucose?
C6H12O6.
C6H12O6. So this is the actual formula for one molecule of glucose. So this is basically your molecular formula. The empirical formula for glucose will be you take the simplest ratio of this. So you'll get CH2O. So 6:12:6 is 1:2:1. So this CH2O is the empirical formula for glucose. So molecular represents the exact number of atoms that are there in that particular molecule. Empirical formula represents the simplest whole number ratio of the different elements. Okay. So suppose you're given percentage composition of any particular compound, you can calculate, you can figure out what is the empirical formula of that particular compound. So what you do is first you convert the mass percentage to grams, like get the exact quantity of the elements that you have. Based on that, check how many moles or how many atoms of each element you have. And once you get the number of atoms, you can just get the formula directly. So I'll take an example for this and do one of this. All right. So a compound contains 4.07% of hydrogen, 24.27% of carbon, and 71.65% of chlorine. Its molar mass, it's 98.96 grams. What is the empirical and molecular formula? So how would you do this? I'll on the whiteboard. So the percentage composition that you're given, you know that the elements that are there are hydrogen, carbon, and chlorine. So the percentage compositions are 4.07%. Carbon was 24.27%. And chlorine is 71.65%. Okay. So based on this, what is the mass of each element present in this compound? Can you calculate that?
Final mass that was given.
The mass that is given is molar mass is 98.96. So this is what you're given. You need to find empirical and molecular formula. Yes. This is 4.07%, Rishabh, not 2. So if you're given that in an analysis of, let's say, 200 grams of the sample or something, you can easily calculate it, but you don't know what is the mass of the sample. You just know the percentage composition. So when you're given simply the percentage and not like an actual mass, assume the total mass to be 100 grams. So if you take 100 grams of the sample, how much of hydrogen would you find? How much carbon would you find? How much chlorine would you find? And we took 100 because you're given in terms of percentages. So calculations get easier that way. That's it. Rishit, the thing that was given was molar mass, not the total mass. the molar mass of the compound was 98.96. All right. So 100 grams mein how much hydrogen do you have? Would you get? Yes, Rishit. Yeah, decimal error, rounding off, there'll be a little bit of difference that way. Yeah. Rishit has sent the answer. Rest of you also quickly calculate. So 100 grams ke sample mein, how much mass of each of these are you going to have? What are you noting, guys? Like, it doesn't require so much calculation.
I miscalculated the first time. I'm doing it again.
Acha, okay. Yeah, Sanat, Smera, Shreya. Okay, the question is, this is what is given, and you need to find. So what is the empirical formula and molecular formula? Yeah. Awesome. Ritu, how did you get like so many decimal places there?
Aren't there that many decimal places?
Like you said,
Was I supposed to round off?
what calculation did you do?
407 into 98.96 upon 100
Why?
to find the mass of hydrogen.
Okay, so you were directly finding for in 1 mole. But in order to calculate like empirical formula, we know that 4.07% is hydrogen. Let's figure out what is the atomic ratio between each of these elements. So for that, let's take the total to be 100, because with 100, you don't have to do so much of calculation. Like later on, it will get easier. Okay. So mass in grams for a total of 100 grams would be 4.07 upon 100 into 100. So it is going to be directly 4.07 grams. Okay. So on that line, calculate the rest of it also. So similarly, what would be the mass of carbon if you assume there to be a 100-gram sample?
24.27. Yeah.
24. Yes, absolutely. Yeah, absolutely, Shreya. So chlorine would be 71.65 grams. Okay. Another reason why I'm asking you to ignore molar mass is you may not be given the molar mass all the time. Here, because you have to find both empirical and molecular formula, you're given this information, but a lot of times you may not be given this. So Yes, correct, Arnav. All right. So this is step 1. Convert the mass percentage to actual grams. Step 2. Rishit is asking, just a small doubt, can't we take molar mass as the mass? I just mentioned, Rishit, like you won't be given this information always. Some questions you'll be given, some questions you may not be given. So you need to be able to figure this out even without this, right? So not always.
So we just assume that it's 100 grams.
Yeah. So sometimes you will be given in a 50-gram sample, these are the percentages. In that case, since you're given the mass, like you can directly use that. If you're not given, for convenience sake, take 100 grams. That's it. If it's given, yeah, you need to check the mass of the sample. You don't just take any mass that's given in the question. So step 2, figure out the number of moles of each element. Like indirectly, you're checking how many atoms of hydrogen, how many atoms of carbon, how many atoms of chlorine. So how many moles of like what calculation should I do to figure out the number of moles of hydrogen in 4.07 grams?
Divided by the mass of hydrogen.
Correct. So 4.07 grams divided by, what would be the mass of hydrogen?
1.
1.
1 divided by 1. Similarly, calculate number of moles for carbon and chlorine also. So 24.27 divided by 12 and 71.65 divided by a mass of chlorine is 35.5.
Do you round it off or do you take like a decimal figure?
Round it
you're
off to
dividing it by 12?
1 or 2 decimal places, yeah. Okay, so this 4.07, 1 decimal place approximately equal to 4. Carbon, Rishit says 2. So approximately it will be about 2. And chlorine. 2.02 you're getting, okay. 2.07, keep it here, right. And this is going to be
2.01.
2.01 approximately, okay. So if I were to approximate it 1 decimal place, it's like approximately 2, 4, 2 and 2, right? So what will be the formula of this particular compound? So that compound contains 4 moles of, gave us 4 moles of hydrogen, 2 moles of
1 is to 1.
2 is to 1 is to 1, yes. So the empirical formula for this, so since this is the ratio of the number of moles, matlab indirectly that's the number of atoms of hydrogen, carbon and chlorine that you're getting. So can you figure out what would be the empirical formula?
CH2Cl.
Huh?
CH2Cl.
CH2Cl? Why? How?
The empirical formula.
C.
It's just 2 atoms of
Oh, sorry. Yes,
hydrogen.
CH2Cl. Correct. Yes. 4 is to 2 is to 2. So that's CH2Cl. So carbon is to hydrogen is to chlorine is 1 is to 2 is to 2. Yes. So this would be the empirical formula. That's how you figure it out. So based on the percentage composition, you are figuring out the number of moles or number of atoms for each element. So that'll give you the ratio of that. So based on the empirical formula, what should be the molar mass of this compound?
Twelve plus 2
79.5.
plus 35.5.
Yeah. What,
79.5.
I think it's 79.
43 point.
Plus 2 plus 35.5. 40 what?
43.5.
49.5.
49.5.
49.5. Right. 49.48 Arnav said, yes. Okay, that's quite accurate. Oh, you got it based on this. So CH2Cl formula is 49.5, but what, like, this is the grams is the molar mass as per the empirical formula, but actual molar mass is 98.96, which means that, what do you think should be the actual composition of the molecule?
Do you take like double the amount? So
double.
C2H4Cl2.
That's exactly it. So actual thing has double of whatever the base simplest ratio we have. So the actual molecular formula will be C2H4Cl2. So double of this. Okay. So did you get the hang of this? Like what we did, why we did it, make sense?
Yes, ma'am.
Yeah. Sanat, Rishit, Ritisha, Adit, Shreya, make sense?
Yes, ma'am.
Okay. Don't just
Yes.
say it like if like some of you still look a little doubtful. So if there's any question, any step you didn't understand, or if you want to go over the whole thing, let me know. Pakka? Yes? Okay. So I'll give another problem based on this. Okay. I think this will be the last thing that we do today. Remaining part of stoichiometry, like dealing with equations and reactions, we'll do it next class. Okay. All right. I'll give another problem. All right, give me 2 minutes, guys. Just... Rishit is saying if we take the molar mass, we get the more accurate answer, right? There's nothing called more accurate. Like you still figured out the formula, right? Like that's the intent. So if in this particular case, because you're given this, you would have, again, the ratio would still be the same. Like you'd get the number of atoms in 1 mole of the compound.
The only reason we got it different was because we took 100 grams, right?
Yeah, the masses were a little rounded off. So yeah. And also the atomic mass also, we didn't take the exact accurate values. Like we didn't take 12.001 or yeah, that sort of thing. So there's a lot of round off estimation there. So that leads to this. Okay, statements on law of definite proportions, law of multiple proportions, and stoichiometry, yes. Okay. All right. So question from your workbook. Is it visible, like the font and all, or should I zoom in a little?
It's
It is
visible.
visible.
Visible? Okay. Look at 1.1.42, number 42. Second part. So compound on analysis gave this composition. So sodium is 14.31%, sulfur is 9.97%, hydrogen is 6%, oxygen is 69.5%. Calculate the molecular formula, assuming that all the hydrogen present in the compound is present in combination with oxygen as water of crystallization. Oh, this has water of crystallization and all that. Like, let it be. We'll do this a little while later. It has water of crystallization. How many of you remember water of crystallization?
It
What
is
is-
the
What?
It's like the
Salt,
water,
I was
it's present
defining.
with the salt.
Yeah, like it's there with the
salt
salt in the
present
crystal.
in each formula unit of water.
No, it's a water molecule present in the ionic structure of the salt. It's the other way around. Yeah. Okay, do 43 instead. The stop set empirical formula. So that's pretty good. So again, it's carbon, hydrogen, oxygen. You're given the percentage of carbon, percentage of hydrogen, or percentage of oxygen. Calculate the empirical formula. See here, you're not given the molar mass or molecular mass. So you can't calculate the molecular formula as such, but yeah. This carbon is 34.6%, hydrogen is
But in
3.85.
this, we don't need the molar mass since we've already been given the percentage, right?
Yeah, and you only need to calculate empirical formula, so you don't need.
Not the molecular.
Yeah.
Ma'am, are we taking this as oxygen gas?
No, oxygen
Mm.
atoms, because here it's part of the formula, right? So if it's independent element, then you have to consider gas. But here it's part of the thing, so individual oxygen atoms. Oh, Rishit's already did it. Okay, it's either. Let me calculate it. I'll do it with you guys. Let's see. I guess using calculator, or are you doing the calculations yourself? Is any of you using the calculator, or
We're doing it manually.
you're doing it manually? Ah,
Doing it on the notebook.
okay. Such good kids you guys are.
So in this also we round it off, right?
Yeah. Okay, Ritu has sent it. Rishit, this side, like you sent me two of them. So which of it is it? And why do you get two different ones? Ah, interesting. Different answers. So Kaveri, you got the ratio, right? Now just apply it to the symbols here and form the empirical formula. Like send me things like C2H or C2H2O2 or like whatever you got. Okay. Smera and Ritu got the same thing, but Kaveri and Rishit. So when you're rounding off, when in doubt, look at the number. If you get something like 2.89, 2.9, that's closer to
The first
3.
one I got 2.9.
So round it off to 3.
So I did 3.
Yeah. And
second one I got 3.8. Like that was the same thing. 3.85.
So yeah, then that's rounded off to the higher number. But if you get 2.01, 2.1, then you have to round it off to the lower number. Okay. Okay. So that way, most of you are getting fairly similar ones, but minor differences, huh? Okay, the most popular one that you guys seem to be getting is this one. Let it go. So most of you have been getting C3H4O4. Is that right? .9 for the first one, 3.8, like 3.8 for the second one, that's rounded off to 4. And for the third one, it is 61.55 divided by 16. The third is also 3.8. Okay. So that's approximately 3:4:4. Yeah. CH4O4 is the right answer, you guys. So Shreya, you got C3H4O3. Like, how do you get O3 there? What is the value that you got, Shreya?
I got 3.5. I don't know how.
Mm,
So I
61.55 divided by 16. So like division mein hoga. So just check your division there. As long as you did 61.55 divided by 16, you got close like 3 point something. So mostly in the division, just check there. Rishit got it, Kaveri got it. Adat, yeah, you got it 3.344. Ritisha, you also got 233. Okay, so you 2.9, you rounded it off to 2. Is that what happened?
Yeah, no, I forgot to correct it.
Okay.
That was before.
Okay. Smira is 344. Ritu 344. Yes. Other than Arnav, I didn't get answers from you guys.
I sent.
Adit, yes, you sent. I'm so sorry.
Ah,
Smira also sent it. So Arnav, I didn't get from you, no? Arnav, how's it going? And Sanat, I didn't get. These are the two people. Arnav and Sanat, you guys got? Where you at? What's happening? Okay. In the meantime, any of your schools have started, or is it gonna happen second half of May?
For Podar, it
17th
will
May.
start on 17th. Yeah.
Okay. And you guys, Rajans?
Rajan's told it will start in June, but no
June.
date as of
Mid-June.
You haven't gotten it yet. Okay.
yeah.
So what are you guys up to these days? Just having fun, or yes, have something to occupy your time?
Mostly having fun. We studied the entire thing, so who studies now?
You studied the entire physics.